Section 1.7, the scientific method. This is the method that's going to teach you how to think like a scientist. The birth of modern science as we know it began about 300 to 400 years ago, and it's associated with scientists like Galileo and Newton. Ancient natural philosophers did a lot of thinking, mainly only, and so now we have an additional component where we have a development of understanding based upon experimental evidence. Using experiments help us to understand the world around us, and adding to just mere observation, these experiments are designed to help us think about ways that we can describe a process, a phenomena, and also how we can predict from its conclusions things that may happen in the future. So the first thing in the scientific method is to make an observation. When we talk about observation, we think of sight, see, hear, touch, smell, taste. And so we find ways of making these measurements using our senses and, of course, using a system of units and using devices and instruments that will help us quantify this observation. And then we ask a question and we develop a hypothesis or a prediction. Loosely described, a hypothesis is said to be an educated guess. And we guess an answer or the explanation as to, the explanation could be what, who, where, when, how, or why is the explanation that's given for our hypothesis as we develop the hypothesis. Something, what happens, why does it happen, how does it happen? Once we have a hypothesis that's developed, we test the prediction using an experiment. And then from the experiment, we will measure. And from our measurements, we will get data so that we can analyze the results and record the results against the hypothesis and then make a conclusion. So these are the processes that pretty much separated the modern science with science that was done in previous times, as we have a more developed approach to asking questions and making a conclusion. In science, we often use the word theory, and in our everyday lives, we also use the word theory. And those two are different in the way we use them. When we're talking about a scientific theory, we're talking about an explanation that is supported by scientific evidence. That's different from when we talk about the casual use of theory in our everyday language, where we're talking about probably an opinion or a hunch or a guess. Like, I have a theory that this platypus can predict the weather. That's just a hunch. It's just an opinion. It's just a guess. So when we talk about scientific theory, it's not just a theory. It's fortified by facts. Scientific theories don't graduate into laws. In fact, scientific theories and the scientific laws are two different things. A scientific theory explains why something has happened based on a lot of experimental evidence. Scientific law describes what happens. So here's where scientific theory and law sort of come together. The theory explains why the phenomena, and we already said the law summarizes a set of observation that tells what happens. And in this shaded area is where we have evidence or information based on evidence, which can be changed with new evidence. And so here is where the theories and the laws sort of are developed and work together based on experiments, based on new information that's available. They're sort of molded, and we can obtain new theories and laws from that. In the big scheme of things, we have what we call science, which is, as we have been describing, we have what's called bad science, and then we have what's pseudoscience, which you might have also heard, and we'll talk a little bit about pseudoscience. The thing that they have in common is they all have science in their name. Science, bad science. Science is valid, bad science is bad, strong premises. Both science and pseudoscience present sound conclusions, but pseudoscience and bad science can be misleading or fraudulent. Pseudoscience have invalid, weak premises. So the belief that humans are affected by the position of the celestial bodies, for example, a pseudoscience. Crop circles, some believe that these are made by aliens, could be science, sometimes bad science. The face on Mars, a rock formation on Mars that resembles a face and is believed to be evidence of life. Again, it can be bad science, misleading, or fraudulent. And one that's most common now is the Flat Earth Society, which claims that the Earth is flat. It's a flat and it's a disc-shaped. The moon landing is a conspiracy and contends the original moon landing was also fake. One of the things I want you to get from this class is to distinguish between science and pseudoscience. And pseudoscience can often be misleading and often absurd claims of scientific results. So you can test if something is pseudoscience by looking at the academic and scientific background of the person that's making the claim that a certain pseudoscience concept is sound. You can look at the history of review by scientific peers, by professionals and scientists in the field, and what their review of this particular concept is. Look at the participation of this concept in a scientific institution where it stands, as well as in an organization and their stance towards it. Pseudoscience often claimed published in peer-reviewed journal and is independently validated by others. And so when we're trying to distinguish between science and pseudoscience, it's often good to check the source and check what scientific institutions and organizations are saying about this particular matter. And that brings us to the end of chapter 1, which is our chapter on measurements, science, what is science, and how measurements are very important to us when it comes to making scientific discoveries, conclusions, and predictions.